Hello everyone. So the paper we are reviewing is a family of optimal locally recoverable codes. Myself I am Ashwant and my teammate name is Praneeth. So let's get started. Nowadays distributed and cloud storage systems have reached such a massive scale that recovery from several failures is now part of regular operation of the system rather than being a rare exception. In addition to this, storage systems have to provide high data availability to ensure high performance. The simplest and most widespread technique used for data recovery is replication. However, this technique is not used as it entails large storage overhead. We will be using more advanced coding techniques that provide comparable resiliency against failures at the expense of a significantly smaller storage overhead. Although today's storage systems are resilient to several concurrent node failures, by far the most common scenario is a failure of single node, and we will be focusing on this. The repair efficiency of a single node failure in the system can be quantified under three metrics. First one is the number of bits communicated in the network. Second one, the number of bits read, that is the disk I/O. And the final one, repair locality, that is the number of nodes participated in the repair process. Okay, now let's look at the LRC code. A locally recoverable code of length n is a code that produces an n symbol code word from k information symbols, and for any symbol of the code word there exists at most r other symbols such that the value of the symbol can be recovered from them. We refer to such code as n, k, r LRC code. In LRC codes, if a symbol is lost due to node failure, at most r other symbols are used to recover its value. Generally, the local parameter lies in between 1 and k, including both, because the entire code word can be found by accessing k symbols other than the erased symbol. In case of MDS codes, r is equal to k, and it can recover the largest possible number of erased symbols among all n, k codes, but they are far from optimal in terms of locality. Let's define locality in a slightly different way. The code is said to have an information locality R if the value of any of its information symbol can be recorded by accessing at most R other code word symbols. Bound on distance is defined by extending the idea of classical singleton bound. And if a code satisfies this bound with equality, the code is called optimal LRC code. However, when defining the above bound, cardinality of code alphabet Q is not used. While recently bound on a distance was established using Q, and sometimes it is found to be yielding better results. Locality cannot be too small if the codes are required to attain capacity of binary symmetric channel. There are two constructions of optimal LRC codes. First one is two-level construction based on a well-known Gabidulin codes combined with a single parity check r plus 1, r code. And second one is using two layers of MDS codes, a Reed-Solomon code and a special r plus 1, r MDS code. The only known optimal LRC codes till now are for r is equal to 1, k. In this paper, we will be overcoming this shortcoming by presenting a natural generalization of the Reed-Solomon code construction. Okay, let's look at the preliminaries on LRC code. Let A belongs to FQ, consider the set of code words C of I, A is equal to X belongs to C such that Xi equal to A, where I belongs to N. Code C is said to have locality R if it satisfies the below condition. That is for different A, A bar, both CII sets should be different. The set II is called recovering set for Xi. The set of coordinates of the n, k, r LRC code is usually partitioned into r plus 1, r local MDS codes that define the recovering sets of symbols. And the large minimum distance and high rate are desirable features of the code. So let's define bound on this code for an LRC code. Let C be an n, k, r LRC code of cardinality q power k over an alphabet of size q. Then the rate of C satisfies k by n less than or equal to r by r plus 1, where k by n is called Right. The minimum distance of C satisfies D less than or equal to n minus k minus step of k by r plus 2. So code that achieves this bound on the distance with equality will be called as optimal LRC code. So from here on, my teammate Pranit will continue.
As discussed earlier, we know what LRC codes are. Here we see how to construct the LRC codes over a finite field with some assumptions. Here are the assumptions. We assume that k is divisible by r, and we see the construction after removing this restriction later. The second assumption is that we consider that n is divisible by r plus 1. Let's see general construction. We begin with general construction of LRC codes using locality property. The codes are constructed as evaluations of polynomials. Unlike the classical Reed-Solomon codes, the new codes will be evaluated at a specially chosen set of points of the field FQ. The main part of construction is existence of a good polynomial. A good polynomial g of x belongs to FQ of x has a degree of r plus 1, and there exists a partition A is equals to A1 and so on up to An by r plus 1 of a set A belongs to FQ of size n into sets of size r plus 1 such that G is constant on each set AI in the partition. In other words, for all I is equals to 1 to n by r plus 1 and any alpha comma beta belongs to AI, Z of alpha is equals to Z of beta. The below construction relies completely on existence of a good polynomial. For an n comma k comma r LRC code, let n less than or is equal to q be the target code length. A belongs to fq such that size of A is equals to n, and z of x be the good polynomial for the partition on A. For a message vector small a belongs to fkq, take it as A is equals to Aij, I is equals to 0 to r minus 1, and j is equals to 0 to k by r minus 1. We define the encoding polynomial as fi of x is equals to sigma I is equals to 0 to r minus 1 fi of x into x power I, where fi of x is equals to sigma j is equal to 0 to k by r minus 1 aij z of x power j, where I runs from 0 to r minus 1. We call f's the coefficient polynomials. The code word for A is found as the evaluation vector of fa at all points of A. In other words, the nkr LRC code C is defined as the set of n-dimensional vectors as shown here. The set of n-dimensional vectors evaluated with f on every element of A. Elements of set A are called as locations and elements of vector fa of alpha as symbols of the code word. The linear code C defined above has dimension k and is an optimal nkr LRC code as its minimum distance meets the bound mentioned earlier with equality. The local recovery is accomplished as follows. Let alpha be the array symbol belongs to Az, where Az is one of the sets in the partition A. Let C beta, where beta belongs to Az excluding alpha, denote the remaining R symbols in the locations of the set Az. In order to find the value C alpha is equals to Fa of alpha, we find the polynomial delta of x such that delta of beta is equals to C beta. Delta of x is equals to sigma beta belongs to Az excluding alpha C beta into pi of beta dash belongs to Az excluding alpha comma beta x minus beta dash by beta minus beta dash, and we set alpha as delta of alpha. So we use polynomial interpolation from R known symbols in its recovery set. Delta of x is called as decoding polynomial for alpha. Remarks. We can see that construction 1 is just an extension of Reed-Solomon codes as both are evaluation of some polynomial defined by message vector. If R equals k, our construction reduces to Reed-Solomon code. The R divides k constraint can be removed easily as follows. Instead of using the quotient polynomial used above, we can use these polynomials that are mentioned here, where s of k comma r comma a is mentioned here. So resulting encoding polynomial has a degree of k plus step of k by r minus 2. Remaining parts of construction remains unchanged. Construction of LRC codes using algebraic structure of field. The main ingredient for construction 1 are good polynomial and its corresponding partition. We construct g of x using the multiplicative and additive groups of fq. Let fq star is multiplicative group and fq plus is additive group. Let h be a subgroup of fq star or fq plus. The annihilator polynomial g of x can be taken as follows. G of x is equals to pi of h belongs to h, x minus h. G of x is constant on each coset of h. The paper covers many more extensions of the code construction like removing the r plus 1 divides n assumption, but due to time restriction we have focused on selected sections of paper. Thank you.